We've recently been talking about forces, and now we're going to move into talking about work. Now, I know you might have a job and maybe you get paid for the work that you do. Perhaps you produce a product or you provide a service. But in physics, defining work is a little trickier. You know, work is very closely related to energy, and energy is tricky to define too. It's difficult to see. We can typically see the results of energy. We can see the results of doing work. We can see the results of something that has too much energy. Maybe it's bouncing on the walls. Or maybe we can see the results of things that don't have enough energy, like they're hard to get going and they're maybe falling asleep like you after a Thanksgiving meal. But we want to define work and talk about the things that go into that process. So we're going to describe work as a product of force and displacement. But remember that force is a vector quantity and displacement is a vector quantity. And when we take a product, we multiply two things together. So this particular product will be a vector times a vector. Now, it turns out in physics, a vector times a vector can give us another vector, which would produce a third dimension that we would need a thing called a right-hand rule to help us identify which way is that thing going. We can find that using a cross product, or we can take two vectors and multiply them and get a scalar product, and that is using a dot product model. So that's what we're going to do when we're dealing with work. Work is a scalar product. Work is something that has an amount but no direction associated with it. So we're going to solve some problems. We're going to discuss the difference between finding work from a single force, or maybe there are multiple forces that act on an object, and so we can either find the work caused by each force and add those up, or we can find the net force and multiply that by the distance, and we can get the resultant work done either way. And then finally, we're going to talk about springs. And you might think, well, why is that a big deal? All of these other products that we're going to talk about come from forces that are being applied, and we are assuming that those forces are constant or average, but mostly we're assuming they're not changing. And with springs are a special case in physics because you can apply a force on a spring, but as you continue to apply that force, the force varies. And so we have to treat that a little bit differently. So let's jump into this. There's three things that have to happen in order for you to be doing work in physics. One, you must apply a force. Two, the object has to move. There must be a displacement. And three, there has to be a component of the force that you've applied that's in the same direction as that displacement. So this will allow us to, or cause us to have to use our trig sometimes. So consider this farmer that's holding a potted plant, and a couple of forces are acting on this pot. And it says that the force F that's exerted on the pot by the man does work. And you'll notice that that force is a horizontal force. So maybe his hand is kind of behind and supporting the force, the pot, and perhaps that force is applied horizontally and you see motion horizontal, so that does work. And yet there's another force that's acting on this pot. That's the force of the earth pulling the pot down. We call that force the force due to gravity, or the weight of the object. Well, that force is acting down, and yet the object is moving horizontally, and there's a 90-degree angle between those two forces, or between those two events. There is no part of a vertical force that acts in a horizontal direction. And so when these are 90 degrees apart, that force is doing no work. So we said that work is a scalar product. It is force times displacement. Because you have to have a component of that force in the same direction, we say it's F with a subscript x multiplied by the displacement. Remember, force is measured in newtons, and x, that displacement, that's measured in meters. So this unit will come out to be newtons times meters, or as we'll find out in just a moment, there's a derived unit for that. So let's consider if you push a box with 40 newtons of force, and the object has a displacement of 4 meters, then the work that's done by that force would simply be 40 newtons times 4 meters, or 160 newton meters. Because this relationship was heavily investigated by a guy named James Prescott Joule, he figured out that there's a relationship between doing work and producing energy, and so he's given credit for the unit of work, which is also the unit of energy. And you might know that the joule is the unit of energy from your chemistry classes. So 1 Newton meter, as a value of 1 joule. Let's say that as you push that box across, that's not the only force present. Perhaps there's a force of friction. And so let's say that as the box is moving to the left, that there's a friction force that's acting to the right. And that friction force is negative 10 newtons. And we want to know how much work does the friction force do? Well, we would simply multiply the force by the distance. And in this case, we would come out with negative 40 joules of work. So what would negative joules of work do? Well, this would simply take energy away from the object. Positive work would add energy into the object. So if we wanted to know what is the total work done, we would sometimes call this resultant work. We could find the work from each force, so we could say 40 newtons times 4 meters plus negative 10 newtons times 4 meters gives us a total of 120 joules. We can add those works up. Or we could find the resultant work by finding the net force. So we could say that 40 newton force was positive, and that plus a negative 10 newtons, that gives me 30 newtons of a net force. Multiply that by my 4 meters, and I still get 120 joules. So these are two different strategies to solving the same problem. Find the net force, or find the work done by each force and then add those works together to get the resultant work. The last piece comes in play when the force and the motion are not exactly in the same direction. So suppose that you were pulling an object and you were pulling up at an angle, but the object was moving sideways. And this would definitely be the case if you were pulling a child in a wagon. So if you applied a 70 newton force with a 60-degree angle and the object moved a distance of 12 meters, then what we've got to figure out is what piece of that force goes in the same direction as your motion. Well, if we draw a diagram for this, we could see that if the force is applied up at an angle, the horizontal component of that force lying along the x-axis, that would be the adjacent side of our triangle if we concluded x and y. And so we would use cosine to help find that piece of that force. So remember, cosine gives me that adjacent side. And so truly, the equation for calculating work is force times the cosine of theta times the displacement. And in every case, theta needs to be the angle between the force and the motion. And so this gives us the x component of that force that would do the work. So the remainder of these notes are going to give you several problems to practice calculating work from a single force or from multiple forces. And as you follow through them and work through these, I know that you can be successful.